You wake up and a sharp smell of rotten eggs hits your nostrils. You look around wildly and realize the smell isn't coming from your mom's cooking downstairs. It's super hot, and there are giant red clouds churning in the sky. Yikes, you're on Venus! Venus. The planet is named after the ancient Roman deity of beauty and love, but sadly, its smell doesn't correspond with its name. The atmosphere of Venus is made up mainly of carbon dioxide, but thick clouds of sulfuric acid completely hide its surface from prying eyes. Sulfur has a really bad stench, which causes the surface of Venus to smell like rotten eggs. Gross! The atmosphere on the planet is also really hot and thick. The carbon dioxide traps a small amount of energy from the sun that reaches the planet's surface. This greenhouse effect has made Venus one of the hottest places in the solar system. So the good news is, you wouldn't be able to smell the planet's stench, as humans can't survive on its surface. Well, that's a relief. Almost all other planets in our solar system only have a super small selection of different scents on their surface, unlike Earth. But what about our moon? The scent of the moon is similar to something called smokeless powder, which is a propellant used in firearms. Basically, the dust on the satellite smells exactly the same as when a shot is fired. Apollo 17's pilot, Eugene Cernan, says he could smell it straight after removing his suit from the spacecraft. But nobody's exactly sure why it smells like this, as there's zero similarity between the two substances. Smokeless powder is made up of a mixture of two things with very complicated names: nitroglycerin and nitrocellulose. Black powder, its older counterpart, is made of charcoal, saltpeter, and sulfur, which makes it smell in a very specific way, but not like rotten eggs, despite the sulfur content. Moon dust is made up of a bunch of things that primarily come from broken meteorites. This includes iron, magnesium, and calcium, but it doesn't contain either of the things in smokeless powder or black powder, either, for that matter. And what's weirder is that moon dust samples brought back to Earth have been odorless. Experts say the smell could have been the dust reacting with oxygen or water inside the lander. The smell could also be due to the temporary release of charged particles from the sun that had become trapped in the dust. Mercury is the planet closest to the sun, but it doesn't really have a strong smell. This is because the atmosphere is so thin and scattered. Mars. Like Venus, it's another world that doesn't have the best scent ever. It's a good thing we can't breathe its air. The red planet smells like rotten eggs, again, caused by sulfur. If human colonies did move to Mars, it looks like we'd have to burn a lot of scented candles to cover the smell. But the good news is that the sulfur quantities are pretty small, so the smell wouldn't be too overwhelming. Jupiter also has a whiff of eggs, but also smells a bit like it's been mixed with cleaning products. This is because its atmosphere is a mixture of hydrogen sulfide and ammonia. But what you smell basically depends on where you are in the planet's atmosphere. Some regions have higher concentrations of ammonia. This substance is used in a bunch of cleaning products here on Earth. So areas high in ammonia could have that strong burning stench of cleaning fluid. A lot of people also say ammonia smells like a pair of dirty socks that haven't been washed in forever. So it's for sure best to avoid these parts of the planet. Other areas have a lot of hydrogen sulfide, and because it contains sulfur, these parts would also smell like rotten eggs. The third and final scent you'll find on Jupiter is bitter almonds or marzipan, just like the kind your grandma puts on cakes around the holidays. This is in areas where a substance called hydrogen cyanide is most common. Jupiter is the biggest planet in our solar system. It's so big that it's 2.5 times larger than all of the other planets in the solar system combined. It's also the fastest spinning planet in our solar system. Next up, the ringed planet, Saturn. Its atmosphere is made up of about 96% hydrogen and 4% helium. Yes, that's the gas that makes your voice go all squeaky. Both hydrogen and helium are odorless, so Saturn probably doesn't have a strong smell. It does, however, contain traces of our good friend ammonia. That's the smelly gas. Saturn's atmosphere also has a bit of phosphine, which can sometimes smell like garlic or decaying fish. So there might be a slight bad stench in the air. The thickness of Saturn's atmosphere is only 37 min-meters equals 60 kilometers. For comparison, our atmosphere here on Earth is almost 480 kilometers. Saturn also has some of the strongest winds in our solar system. One of Saturn's moons is called Titan, and it has a super odd scent. Its atmosphere is made up of something called benzene, which has really weird effects if inhaled by us humans. It can make us feel dizzy and make our ears ring. It doesn't actually smell that bad though. Its scent is kind of like almonds. Now it's time to take a dive into Uranus. This gas giant has gotten itself a reputation as the smelliest planet in the entire solar system. There's a lot of stinky stuff floating around on the planet, and its upper atmosphere is made up mostly of hydrogen sulfide. Yep, that's that molecule that makes rotten eggs smell so nasty. But the temperatures are so severe on Uranus that you'd pass away even before you've had a chance to smell anything. Uranus's atmosphere is a staggering 392 degrees, 235 degrees Fahrenheit. That's so cold that it would almost instantly freeze anyone. The final planet in our solar system is Neptune, and it's just as cold as Uranus at 373 degrees Celsius, 225 degrees Fahrenheit. Neptune also smells pretty bad. Some scientists say it smells like seaweed that's washed up on the shore. Others say again that it smells like rotten eggs because it contains a bunch of hydrogen sulfide molecules. But like on Uranus, you're not going to have time to take in the nasty smell. As the most distant planet from our sun, it's dark, freezing cold, and has supersonic winds. No one would be able to survive when faced with one of the icy hurricanes, which are constantly raging on the planet. Neptune is the only planet in our solar system that's not visible to the unaided eye. We've covered the planets, but what does space itself smell like? Well, space is mostly a vacuum, which means it doesn't actually contain any molecules, so there's basically nothing to smell. But some astronauts have actually said space smells a bit like fried meat or hot metal. This smell is most commonly reported in the first instance after the astronauts re-enter the spacecraft. They shut the airlock, repressurize, and then remove their helmets. But there are a bunch of theories suggesting that the meat smell isn't actually space. It's either from the equipment operating the airlock or from interactions between space particles and the space suits. Astronaut Tony Antonelli said that space definitely has a smell that's different than anything else. Talking about his fellow spacewalkers coming into the ship, another astronaut, Don Petit, said he noticed that this smell was on their suit, helmet, gloves, and tools. One thing we definitely know that has a smell though is comets. If you could inhale a big whiff of a comet, it's likely going to make you feel lightheaded and maybe even sick. The odor from comets is like a mix of rotten eggs, old smelly socks, almonds, and it'll also have a hint of a biology dissection lab. On the bright side though, the presence of hydrogen sulfide and sulfur dioxide in the scent would block your sense of smell after the first sniff, so at least the stench wouldn't linger. The bad news, nearly all the ingredients that make up a comet's smell are toxic, so you're probably gonna want to avoid coming into contact. This planet, yeah, this one right, shouldn't exist, but it does. A newly discovered planet rotates around a star that's much smaller and dimmer than our sun. The planet, however, is enormous. Such a tiny star couldn't create it, so it's like finding an ostrich egg in a chicken coop. A team at Penn State built a special tool called the Habitable Zone Planet Finder. It's an instrument that's supposed to find planets around dim, cool stars. It's connected to a big telescope in Texas. The tool looks at the light from these stars, which is mostly in the near infrared, beyond what our eyes can see. This gadget can spot changes in a star's speed caused by a planet. If a star movement slightly changes, that means there must be a gravitational pull nearby. Years ago, this technique helped find the first known exoplanet around a star like our Sun. Today, we improved this method to make more precise measurements. Our main goal is to find Earth-like planets. They should be rocky and located in habitable zones, areas around stars where liquid water could exist. The Doppler technique isn't that great at finding Earth-like worlds yet, but works well for cool, dim stars. That's how we discovered the impossible LHS 3154b. Planets usually form in disks made of gas and dust in space. Picture a flat, spinning cloud of tiny particles. These particles come together and stick to each other, creating a flat, rotating disk. Over time, these tiny bits combine to form a solid core. This is a starting point for a planet. Once the core is there, it attracts more dust and even gas like hydrogen and helium. But making a planet this way isn't easy. They need a lot of stuff, mass and materials. This process is called core accretion. Stars are a huge help in that process. Normally, big stars have more gravity, so they can gather more stuff to form planets. But the star we discovered recently isn't very big. It's 9 times smaller than our Sun. A star this small shouldn't have a big enough disk to make a heavy planet. To do that, its disk should have been at least 10 times bigger. But this heavy planet, LHS 3154b, exists. This mysterious planet is 13 times heavier than our Earth. It's similar in size to Neptune. It's about 50 light-years away from us in the Hercules constellation, which in space terms is very close. The planet is also super close to its star, completing 1 year in almost 4 days. This discovery is making scientists rethink their ideas about how planets and stars come into existence. There are new theories coming around. For example, a theory called gravitational instability. It says that, instead of the pieces coming together bit by bit, the material in the disk collapses all at once, directly creating a planet. But even with this theory, it's hard to explain how such a heavy planet could form without a really massive disk. It will take us some time to figure out the truth. This isn't the first planet that makes us doubt our theories. Recently, scientists found another planet called Hala. This planet is orbiting a star called Bakdu, and just like the previous one, it shouldn't really exist. It's way too close to its star. Stars change a lot during their lives. Normally, when a star becomes big and prepares to leave this world, it's called the red giant stage. A star like that tends to destroy or push away any nearby planets, creating a huge mess. Hala rotates around a red giant, and it should have been swallowed or destroyed by the expanding star a long time ago. But it's still hanging there. Even though Bakdu has already started burning helium and shrunk to a smaller size than expected, Hala isn't bothered in the slightest. Scientists call Hala the Forbidden Planet. This discovery challenges what we thought about how planets survive near aging stars. It raises 2 theories. One suggests that Bakdu was once 2 stars, a white dwarf, and a red giant. Hala orbited them both, and they merged before the red giant fully expanded. This allowed Hala to survive because the extra helium from the white dwarf prevented the red giant from growing too much. The second theory says that Hala formed from the debris created when the 2 stars merged. In this scenario, Hala would be a very young planet orbiting an elderly star. Astronomers plan to continue studying Hala and look for more planets like that. Another oddball is called LTT 9779b. This one scares us because it's too shiny. This planet reflects 80% of the light from its star. Regular mirrors reflect from 85 to almost 100% of light, which means that this mysterious planet should look like a rough mirror with aluminum or silver-like reflections. This is another Neptune-sized planet. It's located 260 light-years away from us and was discovered by NASA's TESS spacecraft. It completes a full rotation around its star in just 19 hours. It's so close to its star that it's scorching hot, reaching temperatures over 1,182 degrees Celsius. Normally, planets this close lose their atmosphere and turn into bare rocks. But this one breaks the rules again. This time, We know the secret of its survival. It's because of the planet's shiny metallic clouds, which are made of glass and titanium salt. These clouds rain titanium onto its hot surface. They also reflect a lot of light, preventing the planet from getting too hot and losing its atmosphere. It's like having a mirror shield. This planet's size also surprised scientists. It's way bigger than Earth. Other planets this close to their stars are either much bigger gas giants or small rocky planets. This planet is a smaller gas giant, and scientists didn't expect it to exist so close to its star. This is the shiniest planet ever found, even shinier than Venus, but despite its cool appearance, it's probably not a friendly place for life because of its extreme temperatures and strange metallic rain. And our final rule breaker is a planet called WASP 107b. Scientists discovered it using the James Webb Space Telescope. It's located around 200 light-years away from us in the Virgo constellation. It's also fast and completes an orbit around its star in just 6 days. This is a super Neptune exoplanet. It's similar to Jupiter in some ways, including the same size and scorching hot temperatures. But the main difference is that it's much lighter, weaker, and less dense. This is the least dense planet we've discovered so far. After researching some more, we also found that it has a tail. The helium on the planet extends beyond the transit egress. The planet is slowly losing its atmosphere due to extreme ultraviolet radiation from the star. This creates a comet-like tail. So, it looks like a fluffy comet. But that was just the beginning. The planet's low density, or fluffiness, allowed astronomers to study its atmosphere in detail. They found some surprising things, like water vapor and clouds made of fine silicate particles, which are like really fine-grained sand. The planet's host star doesn't emit a lot of high-energy light, but since WASP 107b is so loose, the light can penetrate deep into its atmosphere. This creates sulfur dioxide, that smell when you light a match. In other words, it's a fluffy planet that rains sand and smells like matches. The researchers think the sand clouds in the atmosphere form in a similar way to clouds on Earth. They just have droplets of sand instead of water. These sand droplets condense, fall, turn into silicate vapor in hot layers within the planet, and then rise again to form clouds once more. And once again, this planet couldn't have formed in its current spot. Astronomers say that it likely moved closer to its star from a birth orbit because it was attracted by some heavier neighbor. It also follows a retrograde orbit, meaning it orbits in the opposite direction to its star's rotation. All these discoveries are changing how we understand planets and their atmospheres, giving us new insights into the mysteries of our own solar system. Imagine an asteroid so full of valuable metals that it could make every person on Earth a billionaire. Well, that's not science fiction, it's 16 Psyche, a massive metallic space rock orbiting the Sun between Mars and Jupiter. It isn't just extraordinary because of its value, estimated at $10 quintillion. That's a figure that dwarfs the global economy many times over. It also has clues about the formation of planets, especially the rocky worlds like Earth. In October 2023, NASA launched the Psyche spacecraft. This mission is to explore this cosmic treasure trove. It's supposed to arrive at the asteroid in August 2029, and astronomers hope that it will give us some insights not just about the asteroid's glittering wealth, but also about how planets form and evolve in our solar system. But what exactly makes Psyche unique? First discovered in 1852 by an Italian astronomer, it was the 16th asteroid people identified, hence its name. It stands out among the millions of space rocks in the asteroid belt for one main reason: its metallic composition. While most asteroids are rocky or icy, Psyche seems to be made primarily of iron, nickel, and possibly even gold and other rare metals. At about 278 kilometers wide, it isn't the largest asteroid. It's easily dwarfed by others like Ceres. But its size is still impressive. After all, its surface area is 165,000 square kilometers, like that of the state of Florida. Astronomers think that between 30% and 60% of the asteroid's surface might consist of precious metals. They also think that this space rock might be the exposed core of a planetesimal. A planetesimal is basically a protoplanet, a large space body in orbit around a star, developing into a planet. And this planetesimal could have grown into a full-fledged planet if it hadn't been destroyed in some catastrophic collision billions of years ago. If this theory is correct, Psyche can give us a unique glimpse into what lies deep within terrestrial planets like Earth, where planetary cores are hidden thousands of miles beneath thick crusts and mantles. Now, remember that spacecraft that went to explore the asteroid? After embarking on its ambitious mission, the Psyche probe will travel a mind-boggling 3.5 billion kilometers to reach its goal. This journey will take nearly 6 years. On its way to the asteroid, the spacecraft will pass by Mars in May 2026 and use the red planet's gravity to slingshot itself deeper into space. This maneuver is called a gravity assist, and it will boost the velocity of the probe and refine its trajectory toward the asteroid. By the time it reaches its goal in August 2029, the spacecraft will be set to orbit the asteroid for at least 26 months. During this time, it will analyze its surface, figure out its composition, and attempt to unravel its history. The probe is equipped with some pretty cool tools. One of them is called a multispectral imager. This instrument will snap high-resolution images of the asteroid's surface. It's supposed to help astronomers to study its texture and composition. Then, the probe has a gamma ray and neutron spectrometer. This instrument will measure the asteroid's chemical elements, including its metal content. A magnetometer will detect a magnetic field, if any, which could confirm Psyche's origin as a planetary core. And finally, an X-band radio system will help determine the asteroid's gravity field, which can offer insights into the asteroid's internal structure. NASA isn't sending the spacecraft to assess the value of the space rock as a mining target. Well, at least, not yet. The main goal of the mission is science. Researchers hope to answer fundamental questions about how planets form and evolve. And this asteroid could help us understand what happens when molten material solidifies into a core. Another question we need answers to is, why did it fail to become a planet? And understanding the history of the asteroid might shed light on why some celestial bodies grow into planets while others don't. While NASA's mission is purely exploratory, it has also sparked interest from the point of view of asteroid mining. With its estimated worth of $10 quintillion, Psyche could theoretically supply enough raw materials to revolutionize industries on Earth. Mining it is likely to be decades away, if it ever happens altogether, but the idea still sounds amazing. At the same time, if the asteroid's metals were somehow brought to Earth, their abundance could cause the value of precious metals like gold to plummet, and it would wreak havoc on global markets. Speaking of valuable resources, let's find out how Earth got its own gold, platinum, and other rare metals. These elements, aka highly siderophile elements, have a cosmic origin story, and it's every bit as dramatic as Psyche's. These precious metals were born in violent cosmic events billions of years ago. Many appeared in colonnae, explosive collisions between neutron stars. These metals were then scattered across space and eventually became part of the gas and dust cloud that formed our solar system. When Earth formed, those metals sank toward its iron-rich core, but not all of them ended up deep inside the planet. Destructive collisions with rogue protoplanets like the Mars-sized Theia, which most likely helped to form the Moon, trapped some elements in Earth's mantle. Recent computer models have explained how this happened. After each major collision, Earth's surface temporarily became a magma ocean, a molten layer of rock. As metals sank through the magma, they reached a partially solid layer that slowed their descent, keeping them in the mantle instead of the core. These metals then moved closer to the surface under the influence of thermal convection. That's what made them accessible for mining billions of years later. While Psyche's metals are all over the news, space has more to offer than just gold and iron. Scientists have discovered, or rather theorized the existence of, different gemstones scattered across the cosmos, like diamonds. The thing is, diamonds are made of pure carbon, and this element is abundant in the universe. On Earth, diamonds form deep in the mantle under high pressure and temperature. In space, conditions for diamond formation can occur in surprising places. For example, nanodiamonds, which are really tiny diamonds, have been found in meteorites. Sometimes they contain gases that give us clues about the early solar system. Scientists believe that it might rain diamonds on our ice giants, Neptune and Uranus. There, high pressures compress carbon into crystalline form. Researchers have also predicted that exoplanets in other solar systems could have gemstones like rubies and sapphires depending on their size and proximity to their stars. Even Earth's moon has its own share of cosmic minerals. Scientists have found some traces of cubic zirconia in lunar rocks, so space might hold even more treasures than we've imagined. But let's get back to the Psyche mission. It might not only reveal the whole potential of space resources, but also underline the issues we could face while dealing with them. For example, mining an asteroid would require the usage of autonomous robots, machines capable of operating in harsh space environments. Plus, we would need efficient transport systems to bring materials back to Earth or process them in orbit. We would need to make sure that mining activities wouldn't damage ecosystems or space environments. There are also legal and ethical issues, like the Outer Space Treaty of 1967. It prohibits any nation from claiming sovereignty over celestial bodies. But with private companies entering the space race, debates over ownership and resource sharing are heating up. And finally, bringing such amounts of metals to Earth could destabilize global markets. So, experts suggest that space resources might be better used in space, for building habitats, satellites, and spacecraft. But no matter whether we ever mine 16 Psyche or not, its exploration will teach us more about the early solar system and the processes that shaped our planet. As of December 1st, 2024, the probe is heading for the asteroid, following the orbit around the Sun. Its journey promises not only to deepen our knowledge of the universe, but also to redefine what's possible for humanity as we reach for the stars. In May 2024, stunning auroras adorning the night sky demonstrated all the power that solar storms emit as radiation, but sometimes our sun does things that are far more destructive. I'm talking about solar particle events. During these events, blasts of protons coming directly from the surface of the sun can shoot out like giant cosmic searchlights. According to records, an extreme particle event hits Earth every 1,000 years or so. It often causes bad damage to the ozone layer and increases levels of ultraviolet radiation closer to the surface of our planet. Luckily, Earth's magnetic field acts as a powerful protective cocoon for our planet, fending off electrically charged radiation from the sun. In its normal state, this field functions like a ginormous bar magnet, with field lines rising from one pole, looping around the planet and dropping at the other pole. This pattern is sometimes called an inverted grapefruit. This vertical orientation of the magnetic field at the poles allows some ionizing cosmic radiation to get through the field as far down as the upper atmosphere. There, it interacts with gas molecules and produces the glow we know as auroras. But over time, Earth's protective bubble changes. In the past century, the North Magnetic Pole moved across northern Canada at a speed of about 40 kilometers per year. Plus, it weakened by more than 6%. Even more shockingly, according to geological records, there have been periods of time, as long as centuries and millennia, when our planet's magnetic field was super weak or entirely absent. But we'll talk about those tragic times later. It's easy to imagine what our planet would look like without its protective bubble if you look at Mars. The red planet lost its global magnetic field long, long ago. And once this field disappeared, most of Mars's atmosphere vanished too. In May 2024, a strong solar particle event hit the planet. It disrupted the operation of the Mars Odyssey spacecraft and made radiation levels at the surface of the red planet rise around 30 times higher than what a person receives during a chest X-ray. The sun's outer atmosphere constantly emits a changing stream of electrons and protons, the solar wind. At the same time, the surface of the star also produces bursts of energy, mostly protons, during solar particle events. These bursts of energy have a connection to solar flares, extremely powerful bursts of electromagnetic radiation that can last from minutes to hours. Protons are way heavier than electrons and carry more energy. That's why they can reach lower levels of Earth's atmosphere, exciting gas molecules in the air. These excited molecules emit X-rays invisible to the unaided eye. Dozens and hundreds of relatively weak solar particle events happen during every solar cycle. Now, let's speak about solar cycles for a minute. You see, from a distance, the sun seems to be calm and steady. But if you zoom in, you'll see that its surface is constantly seething and churning. It keeps transforming from a uniform ocean of fire to a chaos of warped plasma and back again in a repeating cycle. Every 11 years or so, the magnetic field of our star gets tangled up. Imagine a ball of tightly wound rubber bands. That's what it looks like at such moments. And then, at one point, it snaps and flips completely, turning the North Pole into the South Pole and vice versa. Right before this event, the sun steps up its activity. It starts to spit out giant blobs of fiery plasma, emit powerful streams of radiation, and grow planet-sized spots. This period has the name of solar maximum. It's a rather dangerous time for Earth since it gets regularly hit by solar storms. Such storms have the potential to disrupt communications and damage power infrastructure. Even worse, solar storms can harm astronauts working in space and even make satellites crash into the planet. As the cycle ends, it fades back to the solar minimum, and then a new cycle begins. Anyway, back to our solar particle events. Researchers have found traces of extremely strong solar events happening throughout the history of Earth, and some of them were thousands of times stronger than anything our modern instruments have ever recorded. Such extreme solar particle events happen approximately every few millennia. The most recent one occurred around 993 CE. Beyond the immediate effect they have, solar particle events can kickstart a chain of chemical reactions in the upper atmosphere, and these processes often lead to depletion of ozone, which isn't a good thing. Ozone absorbs harmful solar UV radiation, which can damage not only our eyesight, but also the DNA of living beings. Plus, changing the amounts of ozone in the atmosphere can impact the climate. In a recent study, researchers used large computer models to examine how extreme solar particle events affect Earth. They found out that if a solar proton event arrives during a period of time when our planet's magnetic field is very weak, then ozone damage can last for 6 years. And the level of UV radiation might increase by 25%, boosting solar-induced DNA damage by around 50%. And apparently, this dramatic combination of a weak magnetic field and extreme solar proton events happens quite often. And some researchers believe that it may even explain a few mysterious occurrences in the past of our planet. For example, the most recent period of weak magnetic field started 42,000 years ago and lasted for around 1,000 years. This period included a temporary switch in the North and South poles. Several major evolutionary events happened during that time. For example, the last Neanderthals disappeared in Europe, along with the extinction of marsupial megafauna in Australia. Yeah, sadly, we won't see giant wombats and giant kangaroos anymore. One more. Even bigger evolutionary event might also be linked to Earth's geomagnetic field. Multicellular animals appeared at the end of the Ediacaran period, which started around 635 million years ago, and it occurred after a 26 million year period of extremely weak or even absent magnetic field. The rapid evolution of different groups of animals in the Cambrian explosion, about 539 million years ago, might have also been related to high UV levels and geomagnetism. The simultaneous evolution of hard body shells and eyes in multiple unrelated groups could have been necessary to detect and avoid harmful incoming UV rays. A complete reversal of Earth's magnetic poles might have a serious impact on the climate of our planet. Luckily, such flips don't happen overnight. The entire process stretches over thousands of years. Plus, even though the magnetic pole weakens during a pole reversal, it doesn't disappear completely. That's why the magnetosphere continues protecting the planet from cosmic rays and charged solar particles, even though there might be some amount of particulate radiation that will make it to Earth's surface. Our planet's magnetic fields are generated by moving electric charges. If some material allows these charges to easily move in it, it's called a conductor. Metal is a great conductor, and we often use it to transfer electric currents from one place to another. In this case, the electric current is negative charges, called electrons, moving through the metal. The current is what generates a magnetic field. Earth's outer core is made of liquid iron and nickel. In other words, there are layers and layers of conducting material inside our planet. Currents of charges are constantly moving throughout the core, and the liquid metal is also moving and circulating there, generating the magnetic field. This magnetic field, in turn, produces something resembling a bubble around the planet. It's called the magnetosphere, and it's located above the uppermost part of the atmosphere. This layer shields and deflects high-energy cosmic ray radiation, which, otherwise, would be extremely hazardous to people and other forms of life on Earth. The magnetosphere also interacts with the ionosphere, the layer of our planet's atmosphere containing loads of ions and free electrons and capable of reflecting radio waves. The interaction between these two layers and magnetized solar winds is what scientists call space weather. The solar wind is normally mild, and there's no space weather whatsoever. You are driving down the highway, and an 18-wheel tractor trailer is coming up fast behind. You've got to change lanes. You look in the mirror. Is there enough space? And you notice the words on the mirror. Objects in the mirror are closer than they appear. No kidding! It is the same with the Milky Way galaxy. There's another galaxy headed this way, and like the tractor trailer, it's closer than it looks. The Andromeda Galaxy, or M31, as it was labeled originally by Charles Messier in his catalog of 110 fuzzy objects in 1774, is now officially named NGC 122. That's New Galactic Catalog 122. A spiral galaxy larger than the Milky Way, the Andromeda Galaxy is so big and so close that you can see it without a telescope. In fact, it appears with the unaided eye half as wide as the moon. It is estimated that the Andromeda Galaxy contains 1 trillion stars compared with the Milky Way's estimated 400 billion measly stars. To see the Andromeda Galaxy, you must allow your eyes to become dark adapted. This might take about 10 minutes while your pupils dilate to take in as much light as possible. M31 is best seen from late summer through winter when the Great Square of Pegasus, the winged horse, is overhead. Draw a line across the Great Square diagonally upwards from the lower corner star, and then go a little further beyond the square. There it is. But you still won't be able to see how big it is unless you peek at it from the corners of your eyes. If you stare straight at it, the galaxy will tend to fade away. You must use your peripheral vision to see how big the Andromeda Galaxy appears. Peripheral vision, or averted vision, allows you to see light more sensitively at night, but without color. Sailors have used averted vision for centuries to see faint lights out on the ocean or on land. Aristotle used averted vision to observe star cluster M41 in Canis Major, as he described in his book Meteorologica. In a telescopic photograph, the Andromeda Galaxy appears 6 times wider than the Moon because with the unaided eye, we can only see the bright center of the galaxy. A telescopic photograph shows how massive M31 spiral arms really are, and this beast of a galaxy is headed our way. We are looking at a future massive collision of galaxies of, well, galactic proportions. When that happens, humanity may need to relocate to another galaxy to inhabit. Perhaps we'll go to the Pinwheel Galaxy and the asterism of the Big Dipper. How do we know the Andromeda Galaxy is moving toward us? With a tool called a spectroscope. After the camera, the spectroscope is the most important attachment to a telescope. Oh, except for the human eye. Our eyes only see light. You don't have this big horse in your eye. You only have the light being reflected by the horse in your eyes. The same with space. We only see the light coming from there. So if we are going to understand space, we need to understand light. And that was not an easy task for astronomers of the 19th century. The invention of the spectroscope was a big breakthrough in understanding light coming to Earth from space. With a spectroscope, astronomers can tell which direction objects in space are moving, as well as which elements are making the light. When you hear an ambulance approaching, you hear the siren getting louder and higher, and when it passes you and goes away, you hear the siren sound get weaker and lower. The change in pitch frequency depends entirely on the motion of the source. This is called the Doppler effect, after Austrian physicist and mathematician Christian Johann Doppler, who first explained the effect in 1842. The ambulance's siren is not changing its volume. The sound waves are being compressed as it is approaching and stretched as the ambulance recedes. The spectroscope shows that light waves show the same Doppler effect as sound waves. They are compressed as the star or galaxy is approaching us and appear stretched when it is receding. Therefore, the light from an approaching galaxy will appear slightly bluer, blue shift, a slight increase in frequency, and the light from a receding galaxy will appear slightly redder than normal, red shift, a slight decrease in the light's frequency. In 1929, Edwin Hubble, after whom the Hubble Space Telescope is named, published his spectroscopic study of 46 galaxies, the light from all but one of which were red shifted, moving away. Hubble's study provided the first evidence that the universe was expanding. The farther away a galaxy was from the Milky Way, the faster it was moving away. This was also the first evidence that the universe began with a Big Bang. The one galaxy whose light was blue, shifted, moving towards the Milky Way, was M31, the Andromeda Galaxy, the closest galaxy. 250,000 rmph seems a pretty high speed at which to have a collision. That's the speed spectroscopic measurements of the blue shift of Andromeda indicate. It's going to be a big mess when it happens. But when is it going to happen? To determine when the two galaxies will collide, we need to determine the distance between them. And for that, we need, boom, supernovas. Type 1a supernovas are what are called standard candles. Just as we know how bright a candle shines, we know how bright a Type 1a supernova shines. Its absolute magnitude. A Type 1a supernova appears when a white dwarf collapses under the pressure of all the gas it has been gravitationally slurping from a companion star. Looking at the Andromeda Galaxy and measuring the apparent brightness of a supernova in the galaxy, it is possible to calculate its distance away. Because the intensity of light dims inversely with the square of its distance away, which is called the inverse square law, by comparing the apparent brightness of a supernova in the Andromeda Galaxy with its absolute brightness, voila, we get an approximate distance of 2.5 million light years. Since 1 light year is approximately 6 trillion miles, and the Andromeda Galaxy is 2.5 million light years away, even though it is approaching at the speed of about 250,000 mph, we have about 4 billion years before the big collision. So you can wait until after lunch, maybe dinner, to start packing. As an aside, if we see the Andromeda Galaxy as it was 2.5 million years ago, and it has been moving toward the Milky Way all this time, how big in the sky would it appear now? Quite as big as that tractor trailer in your rear view mirror. But do we really have 4 billion years before the galaxies crash? There are several other factors to consider. The minor galaxies that are gravitationally linked to both the Milky Way and the Andromeda Galaxy will be swallowed up up by their host galaxies. Considering the lopsided mass distribution that will result, the galactic collision of the Milky Way and Andromeda will be affected. Some scientists are saying it won't be a direct hit, but more of a sideswipe. And then there's the galactic halos of each galaxy. Here's what Project Amiga has found out about the halo of stars and gas surrounding the Andromeda galaxy. Using the Hubble Space Telescope, researchers were able to observe how the light from bright distant quasars was being absorbed by the mostly invisible gas around the Andromeda galaxy. Look at the results. Notice M31 in the center. If the same is true of the Milky Way, and there is no reason to think it would be different, then the halos of the two galaxies are touching now. The collision has already begun. There is also a question about what effect the dark matter clouds around each galaxy may have on an impending collision, or are having now. But enough of speculation. In 4 billion years, the sun will have increased brightness on its way to becoming a red giant star, and humans will have already found another galaxy to inhabit. Happy traveling, dear humans. On July 23, 2024, Europe's Solar Orbiter spacecraft observed a super powerful solar flare erupting from the far side of the sun. This flare wasn't the most extreme ever recorded, but still, we got extremely lucky this time not to get fried by it. Such solar flares often cause long-lived, raging radiation storms, and if such a storm moves in the direction of Earth, it can lead to worldwide blackouts. Before we go deeper into details of that potentially disastrous solar flare, we need to figure out what exactly this solar phenomenon is. Solar flares occur because the magnetic fields in the atmosphere of our star are moving non-stop. When the sun is approaching its solar maximum, and that's the most active period of its 11-year-long cycle, which is, by the way, exactly what's happening now, its magnetic fields get more and more tangled, making our star look like an enormous ball of tangled rubber bands. They loop around, cross over one another, cut one another off, and then reconnect. Ever seen iron filings sprinkled on a bar magnet? These filings line up along the magnetic lines of force. Like that, the hot plasma on the surface of the sun is at the mercy of the magnetic lines of force. Sometimes, when the magnetic fields interact with each other, some plasma gets disconnected from the fields, and its particles accelerate to immense speeds and send powerful radiation to space. That's what a solar flare is. Other times, our star throws off massive amounts of matter. Those events are coronal mass ejections, CMEs. Just one CME can contain as much as 20 billion tons of material. If that material were rock, it would create a mountain about 4.4 kilometers across and almost 0.8 kilometers tall. The ejected material often travels at a speed of over 1.6 million kilometers per hour. Solar flares and CMEs are the most powerful explosions in the solar system, releasing unimaginable amounts of energy. Solar flares have their own classification according to their strength. The smallest and weakest ones are A and B class. Then there are C and M class solar flares, and the strongest are X class flares. A number from 1 to 9, and in some cases a larger one, accompanies each letter. That's similar to the Richter scale for earthquakes. A and B class flares are too weak to affect our planet. As for C class flares, they may have small, noticeable consequences. M-class flares can cause short radio blackouts at the poles and weak radiation storms that can still harm astronauts. But the most dangerous of them all are X-class flares. There are flares more than 10 times more powerful than X1. That's why the classification of X-class flares can go higher than 9. Now let's get back to that recent solar flare. It was X14 class 1. Now we already know that it means it was an extra strong flare. Other large flares astronomers have detected recently include an X12 solar flare that happened on the 20th of May and an X10 flare that occurred on the 17th of July. All of them have come from the backside of the sun. If we talk of the Earth side of our star, the largest solar flare that has been recorded so far within this solar cycle happened on the 14th of May. It was an X8.7 flare that led to radio blackouts. And a strong geomagnetic storm leading to magnificent auroras all over the world occurred a few days earlier. Powerful coronal mass ejections accompanied this storm. As for the July X-class flare, it was so powerful that it could have ended up tragically for us. Luckily, all that magnetically charged plasma blast that accompanied the flare didn't travel in our direction. If it had, it would have been quite the solar storm. Auroras would have been incredibly impressive and a wee bit terrifying in their magnificence. But at the same time, such a dynamic blast of energetic particles hurling our way could have caused major technological problems and electrical blackouts, like the event in 1989, which severely harmed Quebec's power grid, or a much earlier catastrophe that still managed to cause a lot of harm to the world. I'm talking about the Carrington event, which occurred in 1859 and was the first documented solar flare affecting our planet. It happened on the 1st of September and was named after Richard Carrington, the solar astronomer who witnessed the flare through his own telescope and sketched the sun's sunspots. According to scientists, that flare was the most powerful documented solar storm over the last 500 years. The Carrington event triggered auroras that were visible as far south as the Caribbean. It led to severe interruptions in telegraph services all over the world, even shocking some telegraph operators and sparking fires after discharges from the lines ignited telegraph paper. Another major solar flare that erupted on the 4th of August 1972 destroyed long-distance phone communication across a few states, including Illinois. This event even made the American Telephone and Telegraph Company redesign its power system for transatlantic cables. Now, let's move to March 1989, when two super powerful CMEs triggered a geomagnetic storm, which in turn set off a power blackout in Canada on the 13th of March. This blackout left around 6 million people without electricity for 9 hours. It is said that the flare disrupted electric power transmission from the Hydro-Quebec generation station and melted a few power transformers in New Jersey. And still, this solar flare was nowhere near the power of the Carrington event. The Bastille Day solar storm took its name from the French national holiday because it occurred on the same day, on the 14th of July in 2000. It was an X5 class event that caused some satellites to short circuit and resulted in radio blackouts. It's still one of the most highly observed solar storm events. From October to November 2003, our star unleashed a series of large solar flares and coronal mass ejections, and they did reach Earth and slam into its atmosphere. Those solar storms, aka Halloween storms of 2003, caused aircraft to be rerouted, impacted satellite systems, and led to power outages in Sweden. Besides, the Solar and Heliospheric Observatory couldn't fulfill its functions during this solar onslaught. On the 28th of October, 2003, the sun sent a whopper of a solar flare our way. The fire was so powerful it overwhelmed the spacecraft sensor that was measuring it. The sensor topped out at a whopping X28, but later, scientists figured out that the flare had reached a peak strength of about X45. One more thing that made the Halloween storms so scary was that they happened during a time in the solar cycle when solar activity is usually quiet. That's 2 to 3 years after the solar maximum. According to NASA's statistics, just 17 powerful flares erupted from our star during that time. The sun spewed out another X-class solar flare on the 5th of December 2006. It was an X9 class flare that disrupted satellite-to-ground communications and GPS navigation signals for around 10 minutes. That solar storm was so powerful, it even damaged the solar X-ray imager instrument on the GOES 13 satellite. It sustained damage to several pixels of its detector. In February 2022, SpaceX experienced the terrifying power of our star when a devastating geomagnetic storm destroyed 38 Starlink satellites worth tens of millions of dollars. It happened shortly after they were deployed. Unfortunately, Starlink satellites are especially vulnerable to geomagnetic storms since they're released into extremely low-altitude orbits, between 96 kilometers and 193 kilometers. They also rely on their onboard engines to overcome the drag force and raise themselves to their final altitude of around 563 kilometers over the surface of the planet. The thing is, during a geomagnetic storm, Earth's atmosphere absorbs energy from the storm, heats up, and extends upward. It results in a denser thermosphere, which means more drag, and it can be a serious issue for satellites. That's exactly what happened. The batch of newly released Starlink satellites didn't manage to overcome the increased drag and started to fall back, eventually burning up in the atmosphere. When you explode planets, things get red hot. Atmospheres are stripped away, stuff is flying apart, everything collapses. The world becomes brighter than a dozen suns. You squeeze your eyes shut and cover your ears. Your hair stands on end. The sheer power of a cosmic blast is terrifying. Sometime before the explosion, you're hovering in almost complete darkness. Below, you see the moon, or what you think looks like the moon. The surface of this light-colored sphere is pockmarked with craters left by meteorites. You see huge, steep hills stretching for miles. It's Mercury, and right now, you're going to explode it. As if in slow-mo, you watch the planet fall apart, and then, in the blink of an eye, you see a wall of debris closing in on you. First, giant chunks of rock. Those are all that's left of the planet's solid crust and rocky mantle. The appearance and structure of the debris flying in your direction changes. Now, the stuff looks liquid, like splashes of quicksilver. That's Mercury's metallic core bursting apart. It used to take up 85% of the planet's volume, 85% of Mercury, and finally, it's a firework of solid pieces again. It's the planet's solid core. The explosion is so powerful, it knocks Earth into a different orbit. The sun hiccups and swallows down an enormous cloud of dust. That's everything Mercury has left behind. But don't worry, our solar system won't lose any planets. This whole explosion thing is only a temporary experiment. Once you're done watching the show, you press another button, and the planet gets back together, as if you've hit rewind. You approach the next planet on your way. Its surface is hiding under a super dense atmosphere made up of carbon dioxide. If you decided to land on Venus, you'd watch thick clouds of sulfuric acid pass by. You'd see the planet's surface, reddish-brown, dry, and incredibly hot. You'd probably walk across flat, smooth plains covering 2/3 of the planet's surface. You'd gawk at volcanoes littering Venus, all 1/600 of them. Unfortunately, you won't be able to do that because you pressed the button. Boom! Huge chunks of basalt fly away from the center of the explosion. That used to be the planet's 12-mile thick crust, but 12-18 kilo. Then you spot bright, burning meteors flying toward you at incredible speed. Those are chunks of Venus's molten rocky mantle. The fire rain seems endless, maybe because the mantle was 200 miles thick. But that's not the most massive part of the planet. The power of the explosion forces apart Venus's metallic iron core. This core used to be twice as wide as the mantle. You reach a blue marble of your home planet. What will its insides look like scattered in space? From above, Earth looks pretty. 71% of its surface is blue because of all that water, seas and oceans. There are also areas of green, yellow, and brown and white swirls. You press the button. The planet bursts apart in a hailstorm of rocks. They're what's left from Earth's thin crust and much, much thicker mantle. It used to take up nearly 84% of the entire planet's volume. 84% of Earth. You see the rocky rain change into something way more liquid. It's scorching hot iron and nickel that used to make up Earth's outer core. The metals weren't under enough pressure to be solid. The bang is so powerful that it takes apart Earth's inner core. It used to be a solid ball of iron and nickel. After the pieces fly apart, they follow their own orbits around the sun. The most massive chunks crash into the moon, and some travel further and get swallowed by our star. You can't linger. The red planet is waiting for you. The surface of Mars is covered with rusty-colored dust. The thickness of the dust layer varies from area to area, but in most places, it's 7 ft thick. The ground is colored gold, brown, tan, and even greenish. The hue depends on the minerals that make up the soil. The planet's surface is rocky. It's covered with dry lake beds, craters, volcanoes, and canyons. Bang! Mars is a rocky planet. You have to dodge mountain-sized chunks of crust made up of volcanic basalt rock. What you see next looks as if you've blown up huge amounts of soft, rocky toothpaste. That used to be Mars's mantle, composed of oxygen, silicates, and other minerals. And then the flying pieces get solid again. Ah, it's the planet's core's turn. It was solid, made mostly of iron, nickel, and sulfur. Billions and trillions of fragments of all sizes, from a small moon to pieces several feet wide, get launched in all directions. But only very few parts have enough momentum to leave the solar system. The whole event slightly changes Earth's orbit, and the temperature on our planet goes up by 18 IF. You leave rocky planets behind and close in on the first gas giant on your way. It's Jupiter. Thick brown, yellow, red, and white clouds hide its surface. They make the planet look colorful and beautifully striped. You hit the button. This time the view is different. Instead of chunks of solid crust, you see jet streams of gas accelerating from the planet's center. It's what used to be Jupiter's atmosphere, made up of hydrogen and helium gas. In no time, the matter hurtling away to space turns liquid. That's hydrogen changing its form under immense atmospheric pressure closer to the center of the planet. A bit later, the liquid is already a mixture of metallic hydrogen and helium. And finally, something solid. It was probably Jupiter's core, 14 to 18 times the mass of Earth. The gas giant's diameter was about 90,000 miles, but the blast lasts no more than half a second. The explosion of Jupiter is so strong it evaporates smaller planets like Mars and Earth. The Sun remains pretty much untouched. It gets hotter and kinda unstable for a bit, but it doesn't last long. The next gas giant on your way is Saturn. At first sight, it looks as if the planet has a surface. The seemingly solid yellowish-brown sphere is surrounded by layers of clouds. Saturn's trademark rings are awesome and colorful. Gray, beige, and tan. They're actually groups of tiny ringlets that are made up of floating chunks of water ice, rocks, and dust. These chunks range in size from specks to massive skyscraper-sized pieces. While orbiting Saturn, they keep colliding, and larger pieces get shattered. You're surprised to see that the rings aren't perfectly round. They have bends caused by the gravitational pull from the nearby moons. 53 of them are confirmed. Titan, an icy world bigger than our moon and even Mercury, is the largest. What you see looks eerily similar to what happened when you exploded Jupiter. There's only one difference. Saturn's rings break apart, sending rocks and ice flying into space at incredible speed. The largest pieces crash with the planet's moons, wiping away the smallest of them. You see streams of gas, mostly hydrogen and helium, with a bit of methane, ammonia, and water. They're moving at breakneck speed away from where the center of the planet used to be. After that, splashes of liquid matter. That's liquid hydrogen that later turns metallic. And finally, the chunks of the solid core made up of rocky materials. You're looking at a beautiful blue-green sphere of ice giant Uranus. The planet gets this unusual hue when the light from the sun gets reflected off the planet's surface. Plus, Uranus's atmosphere is mostly hydrogen and helium, with traces of methane gas that absorb the red light. Anyway, bang! This time, it's massive blobs of ice that are hurtling in your direction first. They used to be the part of the planet's ice mantle that once made up 80% of the planet's volume. But why does this ice look liquid? On Uranus, frozen liquid isn't solid like on Earth. Ice is a hot, dense fluid made up of water, ammonia ice, and methane. It's often called the water-ammonia ocean. After the bizarre ice rain, you see solid pieces of the planet's rocky core. It used to be small, no more than half the Earth's mass. Some of Uranus's moons get pulverized in the explosion, and several even get ejected out of the solar system. The explosion also slightly shifts Neptune's orbit. And the last planet on your way. Neptune looks blue because of a layer of swirling gas and permanent clouds. No time to linger. Boom! The planet doesn't have a solid surface. That's why after pressing the button, you see Neptune's liquid mantle bursting. It looks like a water-filled balloon thrown down from the 50th floor. This sends splashes of water, ammonia, and methane ices away into space. It's followed by lava-like remains of the planet's mantle. It used to be liquid, red-hot, and rich in methane, ammonia, and water. That's what's left from Neptune's solid core, made up of iron and other metals.
Ever wondered what it would be like to hear the sound of a black hole? NASA's got you covered. Here is a screaming black hole. Screaming in space? I thought in space no one can hear you scream. Well, let me explain. Using a telescope, NASA examined the movements of hot gas in a cluster of galaxies in 2002. Then they converted what they found into a sonification. The sound, how can I put it politely, wasn't appealing, but that's okay. After all, you're able to hear the noise hot gas produces in a cluster of galaxies 250 million light-years away. Hey, how would you like to hear the sound gas produces right here on Earth? Never mind. Sound waves already existed over there in the gas cluster, so experts just rescaled them to the range of human hearing. This is how they converted the input coming from the telescope. The principle is universal. In our atmosphere, we can hear stuff because pressure waves move through a medium like liquid or gas. Sound waves in these galaxies can also move because they're surrounded by gas. What does it have to do with black holes? Well, the thing triggering those pressure waves in the cluster is a giant black hole. To be more precise, it's a supermassive black hole that weighs millions of times more than the Sun. Wow. Experts still don't fully understand the relationship between supermassive black holes and the clusters surrounding them. They only know that these two evolve together. They're interrelated. The cluster feeds the black hole with new material and so on. And in return, the black hole heats the cluster. That's all we know. Now, this made me wonder how large the biggest black holes are. There are 4 types of black holes: stellar, intermediate, supermassive, and miniature. Naturally, the biggest ones fall into the category of supermassive. The largest black hole in the universe we've discovered so far is about 66 billion times larger than the Sun. It's one of the brightest objects in the universe. Astronomers keep scanning space and finding new black holes. But have you wondered when the first black hole was spotted? It was discovered by different researchers independently in 1971. Scientists first confirmed that these objects were formed from the remnants of massive stars. After a black hole appeared, it then consumed all the nearby objects. Here is a quick recap of how these space objects work. Their gravitational force is super strong. Nothing can escape a black hole after crossing the event horizon. Black holes eat everything, just like me. I mean, even light gets trapped inside them. What's even cooler/scarier is that the laws of time and space become distorted there. If you were falling into a black hole, you would realize that time slows down there. Einstein explains this in his famous general relativity theory. In very, very basic terms, time gets affected by how fast you are moving at extreme speeds. NASA has discovered a rapidly growing black hole, but don't worry, the world isn't in danger. This black hole has been in front of the eyes of astronomers this whole time. It's in a region of a well-studied sky field. Astronomers say that this hole formed 750 million years after the Big Bang, the birth of our universe. So why are black holes so bright? Well, that's a bit ironic. When I defined this space phenomenon, I said that black holes were so dense that even light got trapped there. But ask any astrophysicist, and they'll confirm that black holes are among the brightest objects in space. That's because black holes don't exist alone. They sit at the centers of galaxies and are usually surrounded by clouds of hot gas. And these clouds create cosmic auroras around black holes. I must mention, though, that you can't see a black hole directly. What you see is actually the effects it has on its environment. For instance, you can see space objects being ripped apart by a black hole. Remember when the first time ever silhouette image of a black hole was shared with the public in 2019? Proof, you fellas. You wouldn't really see the black hole if there was no orange ring. Why is the ring orange and not green or purple? The dark shadow inside is the shadow of the black hole. The glowing orange of the bright ring in the image isn't the real hue of the gas. I'm a little heartbroken here. It's a representation picked by researchers to depict the brightness of the emissions. A scientist explained that yellow is the most intense emission, red is less intense, and black has little or no emission at all. In the optical range, this ring would likely seem white, perhaps tinged with blue or red. Now, spaghettification is a real word. That's an astonishing ability black holes have. If a giraffe fell into a black hole, it would stretch into a long spaghetti-like strand. On Earth, a giraffe's legs are closer to the center of Earth, so they're more powerfully attracted to the surface than the animal's head. This rule works in the animal's favor on Earth, but would work against it inside a black hole. In a black hole, there's extreme gravity. The closer the giraffe's legs got to the center of the black hole, the more the pull of gravity would stretch them. And the closer to the center the giraffe got, the faster its legs would move. But the top half of the giraffe's body would be farther away, so it wouldn't move toward the center as fast as the legs. Here comes the spaghettification. Can we have meatballs with that? No? Okay. The only difference between a black hole and our sun is that the center of the hole is made of super dense material. It provides the black hole with a strong gravitational field that can trap everything, including light. This is why we can't see black holes. Did you know that, theoretically, you could turn anything into a black hole? For instance, if you shrank the sun to approximately 4 miles across, you would compress the matter inside to an extremely small size. This would make it so dense that our star would turn into a black hole. You could do the same with a planet or even your own body. Is there something called a white hole, or is it just a myth? White holes exist in theory. Hypothetically, they function in the opposite way to black holes. Nothing can enter them. Physicists think of black and white holes as yin and yang, or two sides of the same coin. For them, a white hole looks exactly like a black hole, which makes different things come out of it. But the existence of white holes hasn't been proven yet. And how about wormholes? There are so many movies about black holes and wormholes. How many of them are based on reality, and how much is fiction? Some people believe that black holes function like wormholes. You go inside and exit in another part of the universe. Since we still have a lot to learn and discover about physics, no one can prove this theory is wrong or right. Astrophysics says we need to have a solid theory that unifies general relativity with quantum mechanics. Black holes are among the largest structures in the universe, but there might be tiny specimens. The mass of the smallest black hole we know about is only 3 times greater than that of our Sun. Now, apparently, black holes can vanish. Stephen Hawking developed a theory of Hawking radiation. According to it, radiation decreases the mass and rotational energy of black holes, and ultimately they evaporate. This process occurs very slowly, though, if we're not talking about small black holes. Astronomers have discovered an elusive black hole in the neighboring galaxy. What makes this one special is the fact that it's the first dormant stellar black hole outside of our galaxy. This type of black hole is hard to observe because such holes don't interact much with their environment. They don't emit as much radiation as other black holes. Well, back on Earth, what about sinkholes? Well, different physics. Yet, if you cross the event horizon, your whole car can disappear. Whoops!